Hello and welcome back. We'll now dive a bit deeper into clustering. So what is clustering? It's an unsupervised machine learning method that means we don't have predefined labels. And clustering is used to discover structures in data. We want to establish classes so that we need to define like items within a class are closer to each other than items outside this class. However, what does close actually mean? That means we need to define a distance metric. Let's look at those items we have here. Apples are closer related to each other than they are to pears. Right? But we also have meat and strawberries, for example. So in clustering, we define relationships between objects. So to do so, we need to define a distance metric, and the most typically used metric is the Euclidean distance, that is essentially the length between 2 points. Right? And this is what we most commonly use, but there are other distance metrics that are frequently used as well. One of them is the so-called Manhattan distance, and it's literally called this way because of the square layout of the roads in Manhattan. And the Manhattan distance gives us the length between 2 points on a grid. For example, you can imagine that you are a taxi driver and you want to drive the shortest path between two destinations in New York. Let's look at a few clustering algorithms. The simplest one is k-means. It's an algorithm that is based on the Euclidean distance, and we use the data sample to define k-centroids as initial clusters. So here the k is a free parameter, it's the number of clusters, and we need to know this. If we don't know it, we need to either guess or optimize it. It's called a hyperparameter, and it's a free parameter of our model. So the way this works is that we assign a data point to each of the nearest centroids of our clusters, and then we move those centroids about and then assign data points to it and repeat until no more changes are observed after a number of iterations, or we just stop. So essentially we optimize the sum of squares. Right? So we see that which data point is related to which based on the Euclidean distance, and we assign the data points to those clusters. And as we said earlier, we need to define how many clusters we have so that each point within the cluster is closer related to all other points outside the cluster. Let's look at how this works. So we generate some data with 3 overlapping clusters, and from our domain knowledge we know now that we need to find 3 clusters. Of course, in this case it's trivial because we generate the data this way. In a real case we would have to think about how we define this number, the 3. So here we optimize Euclidean distance. That means we have spherical clusters, and this is more or less what we observe if you run the algorithm. If you look carefully, the overlap regions are of course difficult to capture because the algorithm has not really means to know whether one point is, for example, belongs to the black group or the light group. We could also do the same thing with 4 clusters. Here on the left we see that we generated the data with 3 clusters, but this is only really our expert knowledge. The k-means algorithm doesn't know this. For example, we could give it 4 clusters or more. Another approach is called hierarchical clustering. K-means is a spherical cluster and we don't have relationships between those clusters. However, quite often we do have relations between objects and clusters. And this can be done with agglomerative clustering. For example, we can do a bottom-up approach, and each data point starts as its own cluster. And this is what's illustrated here. We can have different types of apples and pears and strawberries in different meats. And then we do this bottom-up approach, and we find that apples are closer related to themselves compared to pears, and they're quite different from strawberries and meat. Well, then if we move up the next level, then all the fruit will belong to one cluster and the meat won't. And if you move up to 1, everything is food, as for example compared to paper. We could also do this top down and start with items and break them apart and analyze the relationship this way. And this can be typically visualized as a dendrogram. A different approach is the Gaussian mixture model. Remember that in k-means we assume that all clusters are spherical, so that each point belongs to a single cluster. In the Gaussian mixture model, we replace the circles by Gaussians, and this is then the Gaussian mixture model, and this accounts for some variance. Essentially, it allows us to handle oblong clusters. and we assign a probability that each point belongs to such a cluster, and the optimization is done with the so-called expectation maximization algorithm. A very powerful clustering algorithm is called DB-scan, which stands for Density-Based Spatial Clustering of Application with Noise. So here we have a few key points. We don't assume that we have spherical clusters. There are also no hierarchies, and we assign the clusters based on the density of points. But crucially, we also allow noise points. In the other algorithms, we always assume that each point must belong to a cluster. Here in this approach, we allow a certain fraction of points to lie outside of all clusters. So how does this algorithm work? We define a core point with a minimum number of points within a radius epsilon. Right? So this is the green square, our core point, and we define the parameter epsilon. This is a hyperparameter, both of them, so we need to tune those. So we define border points. These are the black ones. They are within the radius epsilon. And then we define a cluster around each core point. Now we assign each border point, these are the black ones, to the cluster of the corresponding core point, and we iterate. And then we keep going until we reach a stable configuration. Here we can see what this method does to the data we have generated. So we have the three blobs, and we compare how k-means, the Gaussian mixture model, GMM, and DB-scan behave. So as you can see in k-means, in Gaussian mixture model, we have tuned the hyperparameters to create exactly three clusters, and this is what the algorithms do. DB-scan, on the other hand, doesn't have this as a free parameter, and so we see we have 6 clusters with 2 small satellite clusters, and we need to deal with those. So we need, for example, can tune the parameter epsilon that describes the behavior. We also see in the case of DB-scan that we have a few random noise points where the algorithm cannot distinguish well which they should belong to. And in most applications this is quite sensible, because now the clusters are well separated, and we always expect some natural noise in our data. You can also compare the performance of these algorithms on more complex data. Before we had these 3 blobs, but for example this moon data set, you can see in the XY plane, it's obvious for us how this should be separated. Those half moons are really quite clearly and distinct from each other. However, both the k-means algorithm and the Gaussian mixture model fail to resolve this, and they draw a sort of funny boundary between them. DB-scan, on the other hand, is fully capable of identifying those.